Welcome to NovaSleep. What if the universe never truly rests? That even in its deepest silence, something hidden is still unfolding. Imagine drifting into sleep while the cosmos itself exhales, releasing everything that was once trapped inside black holes, letting time flow backward through invisible gates of light. These are the white holes, the reverse heartbeat of creation, the universe dreaming in itself awake. As your mind slows and your body softens, we'll journey beyond the horizon of ordinary thought, into the calm, luminous edge where space and time dissolve into pure stillness. Let this mystery carry you inward, where every breath mirrors the quiet rhythm of a universe learning to begin again. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you also write where in the world you are watching and what time it is, I love to read it in the comments. 1- white holes as time-reversed twins of black holes. In the mathematics of general relativity, the same equations that describe a black hole also emit a mirror solution that runs the tape of events in the opposite direction. Instead of a region that traps light and matter, there appears a region that refuses to let anything enter and instead pours energy outward. This mirror concept does not rely on fantasy language, but on reversing the sign of time within the solution while keeping the geometry consistent. The result is a space-time that looks familiar in structure yet behaves with an inversion that challenges ordinary intuition about cause and effect. The horizon of a black hole marks a one-way boundary for infalling matter, while the horizon of a white hole marks a one-way boundary for outgoing matter. Nothing crosses inward across that surface because the geometry denies the necessary paths. Unlike a hypothetical engine that chooses to spit out matter, a white hole does so because the shape of space-time leaves no other possibility. That relentless outward flow defines its identity more deeply than any analogy ever could. This twinship also implies a symmetry that touches the heart of physics. If the basic equations allow both swallowing and expelling solutions, then time may not be as one-directional as daily life suggests. Symmetry does not guarantee existence in the wild sky, but it places white holes on equal mathematical footing and invites a search for mechanisms that would select one branch or the other in a real universe. The fact that one branch is seen everywhere while the other hides remains a driving mystery. The practical consequence of this symmetry is a new way to phrase cosmic questions. If there is a process that forms black holes under gravitational collapse, there might exist a complementary process that reveals white holes under expansion or rebound. That complementary process need not occur in the same place or epoch, which leaves room for white holes to belong to the earliest instance or to domains beyond current horizons. The twin idea, therefore, is not a curiosity at the edge of theory, but a lens that sharpens how origins and endings can be linked. 2. The Big Bang as the most ancient white hole. One bold reading of the early universe treats the initial expansion not as a unique event without precedent, but as an extreme example of a white hole outburst. The logic is simple and unsettling. An initial state with incredibly high curvature and low entropy surges outward, carrying matter. Radiation and structure seeds, much like a white hole discharging its content into newly available space. The outward rush resembles the kinematics of a white hole more than any known explosive process inside the later universe. Viewing the Big Bang in this way reframes the question of beginnings. Instead of asking why there was something rather than nothing, the puzzle becomes where the white hole sourced its contents, and how the prehistory encoded the smoothness of the early cosmos. By translating a unique origin into a familiar, albeit extreme space-time solution, the problem becomes one of boundary conditions rather than exception to law. That shift allows known mathematics to carry more of the explanatory load. This perspective also engages the entropy riddle. The early universe looked remarkably ordered despite being incredibly hot, which sits awkwardly with expectations from thermodynamics. A white hole interpretation turns the spotlight on how order can be exported from compressed domains that store information in a highly constrained way. The outward expansion would then act as a delivery mechanism for structure seeds, while preserving global bookkeeping for information that never vanishes. If the Big Bang bears the fingerprint of a white hole, then some relic patterns should remain in the background radiation and in the distribution of large-scale structure. Those patterns would not announce themselves with a label, but would appear as tiny correlations in temperature polarization and matter clustering that standard stories cannot easily mimic. The hypothesis becomes testable in principle because it predicts families of imprints that an ordinary hot start would not naturally leave. 3. Why general relativity permits white holes, yet observations remain silent. The field equations of general relativity are permissive in a way that surprises the first time one meets them. They do not only describe the familiar, but also a space of possibilities that include time-reversed black holes as perfectly lawful solutions. Such generosity is a strength because it reveals hidden symmetries, yet it is also a challenge because the universe may choose only a subset of what equations allow. White holes live in this gap between permission and realization. Observational silence can have several causes that are not excuses, but specific filters. Formation channels may be rare or confined to epochs when the universe was very different from today. Lifetimes may be brief so that by the time the telescopes search the sky, the candidate events have faded to undetectable whispers. Environments may be hostile to signatures remaining clean, and therefore the telltale signals could be drowned by more common astrophysical noise. Another route to silence is selection by initial conditions. The universe might start in a state that heavily favors collapse over rebound, which would populate space with black holes while relegating white holes to negligible probability. In that case, no symmetry is broken at the level of law, but the cosmic story chooses one branch through the choice of beginning. This is not a shrug, but a statement that cosmology matters as much as pure geometry. A final reason involves quantum effects that could destabilize the idealized white hole solution. When quantum fields are added to curved spacetime, certain perfect structures develop instabilities that cause them to decay or transform. If white holes evaporate almost as soon as they emerge, they would remain invisible except for brief bursts that current instruments might pass over without recognition. Silence would then be a measurement frontier rather than a physical impossibility. 4. Time flow near a white hole and the meaning of reverse aging. Time in relativity is not a universal river that sweeps every observer at the same rate. It is a local clock stitched to motion and gravity. Near a white hole, the geometry enforces outward motion in a way that makes familiar descriptions fail. When people imagine reverse aging, they're picturing a personal clock that runs backward, which is not what the equations predict. Local clocks still tick forward for every traveller, while the ordering of events relative to faraway observers can look inverted. The apparent reversal is about causal structure rather than biological time. Signals that would normally be seen as effects may precede what a distant observer would call causes. This statement is subtle and easy to overinterpret. The traveller would not grow younger. Instead, the map of who can influence whom is redrawn so that influence cannot cross inward, while emissions hurry outward along accelerating paths. The surprise lies in geometry, not in a fantasy of rewinding bodies. Gravitational time dilation near extreme objects complicates the picture further. Clocks deeper in strong fields tick more slowly relative to clocks far away. A white hole combines strong fields with forced outward trajectories, which means there is no stable hovering vantage point from which to compare rates. Any attempt to define reverse aging stumbles over the absence of an interior that can be visited and over the fact that proper time remains stubbornly forward. The true lesson is that white holes challenge naive ideas of before and after without violating the rule that local experience remains sensible. The power of the concept comes from how it separates personal time from global ordering. That separation is what allows a universe to host regions where the narrative arrow swaps roles, while life remains bound to clocks that never reverse their tick. 5. Black hole to white hole bridges across hidden regions of space-time. Many solutions of the equations link a collapsing region with an expanding region through a throat that resembles a tunnel. The collapsing side bears the traits of a black hole, while the expanding side displays the defiant gush of a white hole. The bridge between them is not a corridor that ordinary matter can traverse at leisure, but a structure that belongs to the total geometry. It is a connection of histories rather than a passage for spacecraft. The appeal of such bridges lies in how they conserve information at a global level. What enters the collapsing region is not lost to absolute oblivion, but routed through the geometry to emerge in the expanding region as ordered emission. The mapping may be scrambled beyond recognition at local scales, yet the ledger balances when the entire spacetime is considered. This shift reframes debates about loss and recovery. Bridges also give a physical stage for discussing how universes might bud from interiors that observers never see. A collapsing star could create a domain that becomes causally disconnected, and yet births an expanding elsewhere. That elsewhere would not sit in the original space, but would own its independent future while carrying subtle memory of what fell into the parent black hole. The bridge is therefore a story about heritage. Whether such bridges survive quantum corrections is an open problem. Some approaches to quantum gravity suggest that the throat pinches off, while others propose that a bounce replaces the singular core. Both options still allow a mapping from collapse to expansion. The fine print decides whether the mapping is sharp or statistical, and whether any observable trace can survive across the divide. 6. Could every black hole open as a white hole elsewhere? One program in theoretical physics treats black holes as seeds of expansion that continue on the far side of an unreachable boundary. If that view is right, the cosmos may contain countless offshoot domains that began as white holes fed by collapse in parent regions. Every event of gravitational trapping would then carry a hidden birth certificate for a new expanse. The night sky would be a forest of gateways whose fruits remain forever out of reach. This idea dissolves the fear that information dies at horizons. Instead, information would be exported beyond the causal boundary into a future that belongs to the offspring universe. Conservation would hold without any need for violations of quantum law. The price paid is a humility about what can be recovered by observers who stay in the parent space. A consequence of this picture is an economy of beginnings. Rather than a solitary genesis, there would be a branching tree that spreads across levels of reality. The structure would echo biological reproduction without invoking metaphorical language. Each branch would carry imprints of its progenitor while developing unique large-scale features through its own dynamics. Testing this view is challenging because by definition the offspring is causally sealed off. Indirect clues could appear in patterns of black hole demographics or in the distribution of fundamental constants if branches sample different settings. The thought is ambitious, yet it forces clarity about what physics demands and what it merely allows. 7. White holes as engines behind early cosmic inflation. Inflation refers to a very early phase when distances doubled at a furious and accelerating pace. Standard treatments invoke a special field with a plateau-like potential that drives rapid expansion. A white hole viewpoint offers an alternative engine. Instead of adding a new field, the expansion is sourced by energy released from a rebound event whose space-time geometry naturally accelerates outflow. Such an engine would have to reproduce the near uniformity of the early cosmos, while adding tiny variations that later grow into galaxies. The white hole mechanism can imprint fluctuations because quantum fields in curved spacetime experience amplification when horizons form and recede. The statistics of those fluctuations would be the decisive test. They must match the near-scale invariant spectrum measured in the background light with only gentle departures. A white hole-driven expansion could also explain why inflation ends gracefully. As the geometry relaxes from extreme curvature, the outflow loses pressure, and the universe transitions into ordinary expansion with radiation and matter. This handoff does not require fine-tuning. If the geometry itself dictates the timeline, the end of the white hole phase becomes the handover event that starts familiar cosmic history. The burden on the theory is to connect parameters to observables without free invention. The duration of the outflow sets the number of doubling steps and therefore the largest patterns visible today. The strength of the outflow sets the amplitude of the fluctuations. If a consistent set of numbers fits the sky, there would be a serious case that inflation was the public face of a hidden white hole eruption. 8. White hole outflows and the arrow of time. The arrow of time is often linked to entropy, which tends to increase. A white hole confronts this link by expelling material in a highly directed pattern that can look more ordered than the compressed state that preceded it. The tension is resolved when the accounting is done for the entire spacetime rather than a local snapshot. Entropy can still rise globally even if pockets of apparent order are exported into an expanding region. The arrow may then be tied not only to disorder, but to boundary conditions that privilege certain directions of influence. A white hole fixes influence to run outward, which sets a direction as surely as a broken glass sets a story of cause. This is not a violation of any law, but a statement that geometry can pin an arrow as firmly as statistics can. The white hole becomes a physical anchor for temporal orientation. Another layer of the arrow involves records. For an arrow to be felt, there must exist traces that persist. Outflows lay down records in density waves, radiation patterns, and elemental ratios that survive as fossils for billions of years. Those records guarantee that the direction remains legible long after the event ends. The white hole acts as a recorder as well as a source. This view gives a concrete setting where time asymmetry emerges without special pleading. It is not that time itself flows with a preferred direction everywhere. Rather, certain structures embed a direction through their one-way behavior. When many such structures populate reality, the result is a pervasive sense of forwardness woven from many local threads. 9. Information recovery through white hole emission. The debate about information in black holes arises because classical pictures suggest that everything falling in becomes forever inaccessible. If a white hole stage returns material in a highly correlated stream, the ledger can balance. The correlations would be subtle and distributed across the entire emission, which means that naive measures could miss them, even though the information is genuinely present. Quantum theory demands that evolution preserve information. A white hole phase offers a path that honours this demand while respecting the practical irretrievability that observers experience. The difference between impossible and impractical is crucial. The stream might be so scrambled that reconstruction would require resources beyond any feasible civilization while the principles remain intact. In such a model, the spectrum of the emission would deviate slightly from a perfect thermal bath. Tiny structures in frequency and time would encode the history of what once fell in. These structures would be too fine for current detectors, but conceptually they exist. The law that nothing is lost would then be a statement about perfect bookkeeping that human instruments only approximate. The conceptual gain is large. Instead of a paradox, there is a pipeline. Instead of a wall, there is a loop that closes very far in the future. The idea does not trivialize the difficulty, but it moves the problem from metaphysics into physics, where predictions about correlations can be made and in principle tested. 10. Wormholes with a white hole exit at the far mouth. A wormhole is a bridge that joins distant regions. If one mouth behaves like a black hole that accepts matter, and the other behaves like a white hole that emits matter, the structure functions as a one-way channel. The passage is not a tunnel carved through ordinary space, but a short route through geometry that reduces distance in a way no road could mimic. The white hole role is essential in allowing content to appear at the destination without an entrance from the local side. Such a channel has immediate consequences for the ordering of events. Signals could arrive in regions that have no visible source nearby. To local observers, the emission would look spontaneous. Only by mapping the entire geometry would the provenance become clear. The appearance of the white hole mouth would be a lighthouse of unexplained arrivals until the hidden mouth is included in the story. Realizing such wormholes in nature faces severe constraints from energy conditions. Classical matter resists the shapes required to hold a tunnel open. Some theoretical ideas suggest that quantum effects or exotic fields might ease the constraint without collapsing the bridge. If any such structure exists, the white hole mouth would be the conspicuous end, because it sprays rather than swallows. Searches would focus on transients with no accretion signatures and with spectra that deviate from known engines. The combination of sudden appearance, directionless feeding, and unusual polarization could form a fingerprint. Even a single clear case would revolutionize the map of what the universe can connect. 11. Thermodynamic puzzles around entropy released from white holes. Entropy measures the number of microstates that correspond to a macrostate. A black hole hides those microstates behind a horizon, while a white hole would reveal them through emission. The challenge is to show that the count of configurations on both sides matches so that no accounting is violated. If the match holds, the release might even lower local entropy while raising global entropy through the creation of many correlated subsystems. This balance depends on how the microstates are distributed in the outgoing stream. If the flow is nearly thermal, there is little visible structure and entropy appears to surge. If the flow is finely patterned, the visible order can increase even as the total entropy continues to grow when all correlations are included. The key is that entropy is not a single number until the observer defines what is being traced over and what is being kept. Another puzzle concerns the entropy of the horizon itself. In black holes, the area of the horizon encodes entropy. For white holes, the horizon is a one-way surface of the opposite orientation, which complicates the naive translation. The area may still count states, but the flow of area in time points the other way. That reversal forces a rethink of how area theorems apply when emission rather than absorption rules. Thermodynamics survives these puzzles by insisting on full system accounting. No local decrees can defy the total trend once hidden correlations are considered. The white hole becomes a laboratory for sharpening that discipline and for learning how information-rich outflows can coexist with the overall march toward higher entropy. 12. Hawking evaporation as a prelude to white hole rebirth. A black hole radiates solely through quantum effects near the horizon. Over immense durations, this radiation can drain the mass until only a tiny remnant remains. One hypothesis proposes that at this final stage the object tunnels into a white hole state and expels a last concentrated pulse that carries the remaining information outward. The evaporation would then not fade into nothing but culminate in a distinct event. This scenario ties a graceful bow on the story of collapse. The same quantum fields that initiate evaporation also set the stage for the bounce. The timescale is staggering for stellar black holes, yet for tiny primordial ones the finale could occur within cosmic history. That opens observational windows in high-energy transients that last fractions of a second and carry hard spectra. The mathematics behind the tunneling rests on the idea that singularities are resolved by quantum gravity. Instead of an infinite crunch, there is a smallest scale where compression halts and reversal becomes possible. The cost is a small probability at each step that becomes decisive when the mass shrinks to near minimal size. The event is rare for large holes and common for tiny ones. If this picture is right, the sky should host a faint background of dying primordial holes, occasionally punctuated by a bright terminal flash. Surveys sensitive to brief high-energy spikes would be the best hunters. A positive detection would link three pillars at once, which are relativity quantum field theory and the birth of structure. 13. Stability questions for white holes under quantum effects. Idealized white holes can be unstable. A tiny amount of incoming disturbance can grow without bound when traced backward in time in the mathematical solution. This suggests that any white hole that exists in a realistic environment might rapidly transform into a different state or dissolve altogether. The statement is technical, yet it carries heavy physical weight because perfect isolation is rare in nature. Quantum effects could either worsen or heal this instability. On one hand, fluctuations can act as seeds that trigger decay. On the other hand, the same fluctuations can smear out the sharp features that give the instability its leverage. Certain approaches to quantum gravity claim that the would-be singular core becomes a smooth region that resists runaway behavior. Which tendency wins remains an active question. A way to test stability indirectly is to search for steady signals that a white hole would emit if it remained coherent for long periods. The absence of such signals would not be proof of non-existence, but it would constrain models to very short lifetimes. Transient searches then become more relevant than hunts for persistent sources. The sky becomes a stage for fireworks rather than lighthouses. Stability is not an academic footnote. It decides whether white holes can play sustained roles in cosmic evolution, or whether they are momentary flashes that influence only their immediate neighbourhoods. A firm answer would narrow the vast field of proposals and concentrate efforts on scenarios that nature might actually realise. 14. Mini white holes in the quantum foam. At the smallest scale, space-time may behave like a restless sea, with fluctuations that constantly create and destroy tiny structures. In that picture, miniature black holes and white holes could arise as brief features that live and die almost instantly. Their presence would average out at large scales, yet leave small residual effects in the behaviour of fields and particles. Such mini-events would not look like astronomical explosions. They would appear as noise with a very specific fingerprint. The distribution of energies, the correlation in time, and the way different particles respond would all carry signatures of geometry flicker rather than conventional interactions. High-precision experiments that measure vacuum fluctuations might be able to set limits or even glimpse hints. If mini white holes exist, though, they could provide a natural source of rare high-energy particles without invoking exotic astrophysical engines. A tiny flash could kick a particle to the tremendous energy and then vanish. The particle would arrive at detectors long after the source ceased to exist, with a spectrum that reflects the microphysics of the flash. Patterns across many events would be the clue. The concept offers a way to unify restless quantum behavior with the grand architecture of space-time. Instead of treating geometry as a fixed stage, it becomes an actor even at the smallest distances. White holes, then, are not only cosmic titans, but also fleeting whispers in the foam that keep the universe lively at every scale. 15. The geometry of a white hole event horizon. An event horizon is not a material surface. It is a boundary in space-time that separates regions according to which paths light can take. For a white hole, the horizon is oriented so that paths only cross outward. This one-way orientation defines the object more deeply than brightness or colour because it encodes the causal rules that everything must obey in its vicinity. The shape of the horizon responds to rotation and charge in ways that mirror black hole cousins while flipping the direction of allowed motion. Rotation can pinch the horizon and create regions where outgoing paths swirl into funnels that collimate emission. Charge alters the balance between gravitational pull and electromagnetic push, which can change the rate at which the horizon sheds its contents. These are not surface properties but geometric facts. Close to the horizon, the light cones tilt so strongly that even photons prefer outward directions. That tilt is the graphic signature of a white hole. Any object forced close enough will be accelerated outward, regardless of its will or design. The effect is not a force in the Newtonian sense, but a mapping of allowed futures that has no entry choices. Understanding that tilt is essential for predicting spectra and beaming. Far from the horizon, the geometry relaxes and ordinary intuition returns. Yet traces of the horizon orientation remain in polarization patterns and in the timing of pulses created by turbulent outflow. Those traces allow observers to reconstruct the invisible boundary from the shape of the light that escapes. Geometry becomes visible through the discipline of careful measurement. 16. Observable signatures that could distinguish a white hole from a quasar. Quasars are among the brightest and most distant objects known, powered by the accretion of matter into supermassive black holes. Their light, often variable and energetic, floods space across radio, optical, and X-ray wavelengths. A white hole, if one existed, might mimic this brilliance, yet its physical signature would differ in fundamental ways. Rather than feeding on surrounding gas, it would push matter outward without any visible source of infall. The challenge is to separate such a pattern from the noisy background of conventional cosmic engines. The most direct clue would lie in motion. Quasars draw material inward, creating distinctive blue and red-shifted jets as plasma falls and rebounds. A white hole would show only outward motion, with no sign of gravitational feeding or orbiting debris. Spectra could reveal asymmetries in emission lines, where energy profiles lack the hallmark absorption features of infalling gas. In the data, such an object would seem to radiate from nowhere, violating the balance expected of a black hole system. Timing behavior provides another window. Quasar brightness fluctuates through turbulence in its accretion disk, following statistical patterns that repeat across scales. A white hole, having no disk at all, might produce short, impulsive bursts instead. Clean spikes with minimal repetition. Instruments capable of sub-second resolution would be essential for catching these differences, especially at high energies where conventional variability ends. Finally, polarization and jet geometry could distinguish the two. Radiation emerging from rotating magnetic fields around black holes is often polarized in swirling patterns. A white hole's emission, dominated by expansion rather than rotation, could yield linear polarization or chaotic orientations unrelated to a central spin. Detecting these subtleties demands next-generation interferometers and long patience, yet the reward would be nothing less than confirming an entirely new class of astrophysical object. 17. Fast radio bursts as possible white hole eruptions. Fast radio bursts are millisecond flashes of radio energy arriving from remote galaxies. Their sources remain largely mysterious: magnetars, collapsing stars, or stranger phenomena. The concept of a microscopic white hole adds a new contender. In this model, each burst represents a final outcry of energy when a quantum-sized black hole completes its evaporation and flips into a white hole state, releasing pent-up energy as a coherent radio pulse. Such an event would explain several observed peculiarities. The brevity fits with a quantum transition, measured in microseconds, and the immense energy compressed in the radio band suits a conversion of gravitational mass to radiation. Repeaters, bursts from the same location at irregular intervals, could signal a cluster of many tiny black holes undergoing transitions at slightly different times. The randomness of arrival times would follow naturally from statistical decay processes. To test this view, astronomers examine dispersion measures, the delay of radio frequencies across space. If bursts are white hole events, their frequency distribution might exhibit a sharp cutoff imposed by the quantum geometry of their origin. Moreover, polarization could encode information about the curvature surrounding the moment of release, distinct from magnetar patterns. Such markers would turn every burst into a probe of quantum spacetime itself. The idea remains speculative but inspiring. Fast radio bursts show the universe at its most impulsive. White holes offer a framework for that impulsiveness grounded in relativity and quantum theory together. Should even one burst display unmistakable geometric features incompatible with magnetic models, the door to direct evidence of time-reversed phenomena would finally open. 18 gamma-ray flashes and ultra-short energy spikes from white holes, gamma-ray bursts lasting from milliseconds to minutes, already hint at colossal rearrangements of energy. Yet there exist rarer, sub-millisecond spikes, too sharp to fit known astrophysical engines. These might be the breath of tiny white holes discharging their last stores of energy. The conversion of mass into pure radiation under extreme curvature would naturally peak in gamma rays, the most penetrating form of light. In this context, a black hole smaller than a mountain could survive quietly for eons, then erupt when quantum tunneling flips its geometry. The resulting flash would outshine entire galaxies for an instant, leaving a clean afterglow-free signature. Satellites would register a perfect spike, no lingering tail, no precursor, and its spectrum would be unusually narrow. Such precision, if found, would separate a white hole event from collapses or neutron star mergers that display complex multi-stage light curves. Models predict a power law distribution of these eruptions, with the smallest being most common. Detecting them would require instruments sensitive to nanosecond timing and broad fields of view. Some unexplained single-pulse detections in historical data already tempt reanalysis under this lens. The absence of accompanying gravitational waves in those events strengthens the case for a non-merger origin. If confirmed, gamma flashes from white holes would mark humanity's first glimpse of reversed space-time in action. Each spike would represent a boundary crossed, matter reborn as radiation, compression yielding to expansion. It would also demonstrate that the universe recycles information and energy through mechanisms still hidden in its deepest codes. 19 gravitational wave fingerprints of a white hole event. When massive bodies accelerate, they ripple space-time itself. Black hole mergers have already been heard by detectors on Earth. A white hole event, though diverse in behavior, would also send gravitational notes across the cosmic symphony. The pattern, however, would differ sharply. Instead of a slow chirp that rises in pitch as two objects spiral inward, a white hole signal would open with an abrupt peak and decay swiftly, a reverse melody played in space-time. Simulations suggest that the waveform might even contain echoes, brief repetitions caused by reflection from the newly formed horizon's inner geometry. Unlike merger chirps that fade smoothly, these echoes would punctuate the tail of the signal like reverberations in a vast metal hall. Detecting them demands extreme sensitivity and advanced correlation algorithms capable of teasing faint structures from noise. Such fingerprints would also carry polarization signatures indicating expansion rather than compression. The orientation of the strain on detectors could flip relative to expectations from collapse. This inversion would act as a direct geometrical test, a literal measurement of reverse temporal ordering in gravitational waves. If such an event were recorded, its implications would be immense. Gravitational waves cannot be forged by trickery of light or magnetism. They are pure geometry. Capturing an inverted waveform would mean the cosmos truly produces mirror processes, evidence that creation and destruction are symmetrical operations under the deeper rules of space-time. 20. Light paths curved by the white hole repulsion. Gravity is universally attractive in daily experience. Yet general relativity allows configurations where curvature bends light outward. A white hole, by definition, enforces this outward curvature. Photons that graze its horizon would be deflected not toward but away from the center, creating visual distortions opposite to those of black holes. Instead of dark rings and captured shadows, one might see bright halos where light is expelled. This repulsion would alter lensing patterns across distant fields. Behind a white hole, background galaxies could appear stretched outward, their images duplicated in concentric circles rather than bent inward. Such inverse lensing would be subtle, demanding surveys capable of mapping fine distortions over large angles. Algorithms designed to find black holes might even miss them, because the expected convergence pattern is reversed. An additional clue lies in spectral time delays. Light skimming a black hole arrives later because it takes a longer curved path. Around a white hole, certain paths could shorten, making pulses arrive earlier than expected relative to gravitational models. Timing arrays that compare arrivals from pulsars or quasars could thus reveal negative delays. an impossible result under ordinary gravity. Observing any of these effects would confirm that space-time can repel as well as attract. Such discovery would not overturn general relativity, but fulfill its broader potential, proving that gravity is geometry, not merely force. The sight of stars bending away from an invisible center would stand as one of the most counterintuitive and profound images ever captured. 21. Causality questions raised by matter ejected before the source forms. In ordinary physics, causes precede effects, yet the mathematics of white holes allows scenarios where emission is visible before the event that logically creates it. This apparent violation of causality arises because the light cones tilt beyond the ordinary boundaries of time order. Matter can exit a region that, from the external viewpoint, does not yet exist. The phenomenon invites both wonder and careful bookkeeping. To make sense of it, physicists distinguish local causality from global chronology. Locally, every observer still experiences ordered progression. No one sees their own past change. Globally, however, the network of events can loop in peculiar ways, so that an emission recorded today corresponds to a future collapse elsewhere. The universe remains consistent, but its story folds back on itself. Such temporal crosstalk might explain certain unexplained high-energy transients that lack clear progenitors. They could be emissions from future black hole collapses seen prematurely through white hole geometry. Data archives already contain flashes that defy ordinary sequences. Reinterpreting them through reverse time metrics could yield a consistent timeline spanning both directions. The deepest implication is philosophical yet measurable. Perhaps causality is not broken, but two-way, woven into space-time as a bidirectional web. Events could be connected through feedback loops that ensure overall consistency while blurring our human sense of before and after. Detecting even one verified example would revolutionize how time and history are defined. 22. Do white holes demand exotic matter or merely extreme curvature? Holding open a white hole against collapse appears to require unusual conditions. Some models call for exotic matter, substances with negative energy density that counteract gravity. Others argue that geometry alone, if curved enough, can produce the outward behavior without violating known energy conditions. The debate cuts to the core of what makes space-time dynamic. Is matter the sculptor, or is geometry capable of self-sustaining shapes? Exotic matter remains theoretical but not impossible. Quantum fields in vacuum can exhibit negative energies for brief intervals, a phenomenon confirmed in laboratory Casimir effects. If such fluctuations scale up in extreme gravitational contexts, they could stabilize a white hole throat just long enough for emission. However, sustaining them macroscopically appears unlikely, making purely geometric mechanisms more appealing. Extreme curvature, on the other hand, can mimic repulsion through time reversal of the collapse process. When equations are extended beyond singularities using quantum corrections, the inverted solution behaves as an expanding shell without any special substance inside. This approach preserves conventional energy conditions while still achieving outward motion. It turns the requirement from material to mathematical. Future quantum gravity theories may decide the issue by showing whether space-time possesses elasticity that substitutes for exotic matter. Either outcome deepens understanding. If exotic matter exists, it broadens the inventory of the cosmos. If geometry alone suffices, it confirms that curvature itself carries all the drama once attributed to mysterious materials. 23. White holes within cyclic cosmologies of endless renewal. Cyclic cosmologies propose that the universe undergoes repeated expansions and contractions rather than a single beginning and end. Within this framework, white holes play the role of rejuvenating agents, releasing matter and energy stored from previous cycles into the next phase. Each cosmic bounce would therefore be a grand-scale white hole event, a renewal through expansion. Mathematically, this picture eliminates singularities. Instead of an abrupt stop, contraction halts at finite density, then reverses as pressure from quantum effects drives re-expansion. The outward surge mirrors the theoretical white hole behavior, where time flows away from the high-density region. Observers inside each cycle would perceive their universe as beginning anew, unaware of the preceding contraction. Such models elegantly address entropy buildup. If each contraction compresses and randomizes information, a white hole-like bounce can reset the visible order by redistributing energy across new dimensions or degrees of freedom. The global entropy may still rise, but each cycle experiences its own low-entropy dawn, preserving the arrow of time within finite intervals. Evidence might lurk in subtle patterns of the cosmic microwave background, repeated motifs or circular correlations implying pre-existing structure. If these are found, they could signal that we live not in the first universe but in one chapter of an eternal series, every chapter opened by the eruption of a white hole that is the memory of the last universe's collapse. 24. The universe as the interior outflow of a higher dimensional white hole. Some cosmologists extend the idea beyond cycles into dimensional hierarchy. Our entire observable universe might be the outflow region of a white hole embedded in a higher dimensional space. From that parent realm, energy and matter spill through a geometric throat, forming the three-dimensional cosmos we inhabit. The Big Bang would then appear as a local burst, while in higher dimensions, it is merely an ongoing jet. This picture aligns naturally with theories like string cosmology and brain-world scenarios, where extra dimensions exist beyond perception. A white hole in that setting would funnel energy into our brain, inflating it and supplying the raw material for galaxies and stars. What we call expansion could be continuous feeding from the higher realm rather than an isolated event in the past. Detectable consequences might include tiny anisotropies, directional differences in cosmic expansion, if the outflow is not perfectly symmetric. Also, gravitational waves could leak between dimensions, producing frequency gaps or excesses that instruments might eventually resolve. These clues would bridge cosmology and high-energy physics, linking vast scales with microscopic geometry. If true, our universe is not an isolated bubble, but the living plume of a multidimensional fountain. White holes, in this sense, would not be rare objects scattered through space, but the fundamental mechanism that births entire realities, each bubble expanding within its parent's hidden geometry. 25. White holes and the low-entropy beginning of the cosmos. One of cosmology's enduring puzzles is why the early universe had such astonishingly low entropy, a degree of order that defies statistical expectation. If it began as a white hole event, the paradox softens. The interior of a collapsing region contains constrained configurations where energy is packed, but correlations are high, yielding low entropy despite high density. The subsequent expansion naturally increases entropy, aligning with the observed arrow of time. This mechanism treats the Big Bang's smoothness not as coincidence but as consequence. A white hole origin mandates ordered initial conditions because they are inherited from the collapse that preceded it. The outward phase begins with well-defined geometry and minimal turbulence, just what cosmic background data indicate. Entropy rises afterward as structures form, preserving consistency with thermodynamic law. The approach also sheds light on why quantum fluctuations were tiny yet crucial. In the high curvature environment of a white hole, quantum noise would be suppressed except in specific modes linked to horizon dynamics. Those selective ripples become the seeds for galaxies billions of years later. Thus, the smallness of primordial irregularities is a fingerprint of the white hole process itself. Seeing entropy through this lens transforms a metaphysical question into a geometric one. Order at the beginning is no longer a mystery, but the natural boundary condition of a reverse collapse. The universe's youth appears calm not by miracle, but because it was born from the discipline mathematics of time-reverse gravity. By the way, if you like and subscribe to my video, this is the most effective way to support me. 26. Entanglement bridges that pair black holes and white holes. Quantum entanglement links systems so that their properties remain correlated even when separated by vast distance. Some researchers propose that this linkage is not only metaphorical but geometric, forming a subtle bridge that welds a collapsing region to an expanding partner. In this picture, a black hole does not end in isolation, but hands off its informational content to a white hole through a fabric woven by shared quantum states. The bridge is not a traversable tunnel in the science fiction sense, yet it carries structure across the boundary where classical reasoning fails. Such a pairing would explain how information can leave a trapped region without breaking quantum law. The correlations would be distributed across the outgoing stream from the white hole, encoded in patterns too fine for casual instruments to resolve. What appears thermal at low resolution could hide delicate structure that only a full accounting would reveal. The ledger would balance even if observers cannot practically reconstruct the book. Entanglement also changes how we imagine horizons. Rather than hard walls, horizons become relational boundaries whose properties depend on what they are entangled with. A black hole linked to a white hole would inherit constraints that govern the timing and spectrum of any eventual release. The outward flow might arrive with a fingerprint that matches the internal state of the partner object. Testing the idea requires looking for statistical anomalies that betray hidden order. These might include slight deviations from perfect randomness in high-energy transients, or correlations between widely separated events that share no classical cause. Even partial evidence would mark a turning point, showing that geometry and quantum linkage act together to direct the fate of matter and information. 27. Vacuum energy collapse as a trigger for white hole birth. The quantum vacuum is not truly empty. It hosts fluctuations that flicker in and out, carrying energy that can push or pull on space-time. Under extreme compression, those fluctuations may align into a coherent push that halts collapse and initiates a rebound. The rebound does not explode like a bomb. It unfolds as a geometric reversal that looks outwardly like a white hole turning on. This mechanism replaces singular endings with finite minima. Instead of infinite density, the system reaches a smallest possible state where vacuum effects dominate. The pressure from those effects initiates expansion, converting curvature into outgoing radiation and particles. The sequence forms a bridge from a trapped region to an emission phase without invoking exotic substances that violate well-tested energy conditions. If vacuum collapse triggers white hole birth, parameters of the vacuum become cosmic levers. The strength of the fluctuations, their coupling to gravity and their sensitivity to curvature would set the duration and brightness of the emission. This makes the idea predictive rather than decorative. It invites comparisons with measured relics, such as background radiation patterns and primordial element abundances. Laboratory analogues can illuminate parts of the story. Systems where effective horizons appear, including condensed matter setups with sonic or optical horizons, can mimic aspects of vacuum-driven rebounds. Although these are analogies rather than literal reproductions, they allow controlled tests of how fluctuations behave near boundaries. Lessons learned there can guide what astronomers should look for into the sky. 28. Dark energy as cumulative pressure from microscopic white holes. The cosmic expansion is accelerating, an observation often attributed to a smooth background energy that fills space. A different view treats the acceleration as a population effect. Countless microscopic white holes could be flickering in the quantum foam, each contributing a tiny outward push. Alone they would be insignificant, yet in aggregate they might act like a uniform pressure that speeds the expansion. This concept supplies dynamics where a constant would be featureless. The pressure could vary slowly over time if the abundance or activity of the micro-events evolves. That variation might appear as a gentle drift in the acceleration rate, measurable across billions of years. Observations of supernova distances and gravitational lensing maps would then double as a census of micro-white hole activity. The idea also offers a link between the smallest and largest scales. Quantum geometry at the Planck scale would decide the statistics of the flickers, while the cosmic expansion turns those statistics into observable motion of galaxies. If the link is real, one could infer properties of quantum gravity by measuring the expansion history with exquisite precision. Falsification paths are clear. If the acceleration behaves exactly like a true cosmological constant with no detectable evolution, the micro source model would lose support. If subtle time dependence is confirmed, the model would gain ground and prompt a new generation of measurements aimed at mapping the heartbeat of the foam that underlies space. 29. Dark matter as relics of undetected white hole ejecta. Dark matter reveals itself through gravity, yet resists detection through light. One speculation holds that it could be matter expelled long ago from white hole episodes, chilled and diffused into halos that cradle galaxies. Ejecta born in extreme curvature could acquire unusual properties, perhaps forming stable non-luminous clumps that pass through ordinary matter without much interaction. Such a lineage would naturally see large-scale structure. Streams from many ancient events would weave into filaments and knots, shaping the scaffolding upon which gas later condensed into stars. The distribution would remember the geography of eruptions, potentially leaving subtle anisotropies that precise surveys might still uncover. Particle physics experiments would test this scenario by probing candidate particles that match the required invisibility and stability. If the ejecta are not new particles but altered states of familiar ones, detectors must broaden their search strategies beyond standard expectations. The cosmic origin story thus informs the laboratory search, guiding where to look in parameter space. Astronomical evidence could come from lensing maps that trace dark matter directly. If halos contain fossil streams, their lensing patterns would deviate slightly from smooth profiles. Future instruments with finer angular resolution could expose these structures, transforming white hole relics from a poetic possibility into a measurable imprint on the sky. 30. Cosmic voids as ancient white hole blast cavities. Voids are vast regions with far fewer galaxies than average. Standard growth explains them through gravitational evacuation as matter flows into denser areas. A white hole perspective adds a complementary origin. Powerful outflows in the distant past could have swept regions clean, pushing material into surrounding walls and leaving low-density bubbles behind. If voids bear this history, their shapes and internal motions would differ from purely gravitational evacuations. One would expect more spherical symmetry in some cases, and residual outward velocity fields that persist long after the initial push fades. Sensitive surveys of galaxy motions within voids could reveal these signatures as tiny deviations from the expected Hubble flow. The temperature of gas inside such cavities provides another clue. A blast origin would heat gas unevenly, leaving broad regions with temperatures slightly higher than surroundings. Observations of the Sunyaev-Zelman effect, where hot electrons scatter background photons, could quantify this history. Finding even a subset of voids with blast fingerprints would imply that energetic events, possibly tied to white hole episodes, played a role in arranging the cosmic web. The universe would appear less like a passive canvas and more like a landscape touched by ancient eruptions that still shape where galaxies choose to live. 31. Magnetism seeding by white hole jets. Magnetic fields permeate galaxies and clusters, yet their origin remains partly unexplained. White hole jets could supply seed fields by launching charged particles through twisting geometries that convert motion into magnetism. These seeds would grow through turbulence and dynamo action, eventually becoming the large-scale fields astronomers map today. The mechanism exploits rotation and shear in the outflow. Even modest spin can align currents that wind magnetic lines into helical structures. As the jet expands, these structures spread across intergalactic distances, planting magnetism where none existed. Later processes amplify the faint imprint until it becomes a backbone for cosmic plasma. Observational support would include polarized relics in the outskirts of galaxies and clusters, regions where few other engines operate. The orientation of these relics could align with ancient outflow axes rather than with current galactic rotation. Radio surveys already find puzzling polarized patches in remote environments. Reinterpreting them through white hole seeding could unify scattered anomalies. If correct, the story of cosmic magnetism becomes part of the larger narrative of time-reverse structures. Fields that guide, starbirth, and control cosmic rays would trace their ancestry to events where space-time itself inverted its role from trap to source. Magnetism would be another fossil of a deeper geometric drama. 32. Galaxy formation catalyzed by white hole matter streams. Galaxies require initial overdensities to gather gas and ignite stars. Streams from white holes could provide such overdensities with directional coherence. Unlike random fluctuations, these streams would deposit matter along preferred axes, encouraging elongated protostructures that later relax into disks or spheroids depending on merger history. This mechanism offers a route to early massive galaxies that otherwise seem to form faster than expected. Concentrated delivery of gas can jumpstart star formation and black hole growth without waiting for slow hierarchical assembly. The observed maturity of some galaxies at high redshift would then reflect targeted feeding rather than gentle accretion. Testing the idea involves mapping alignments. If many galaxies share a common orientation rooted in ancient streams, their spins and satellite distribution should reveal patterns that exceed random chance. Surveys of galaxy spins across large volumes can search for such coherence. And early hints of alignment have already sparked debate about their origin. Confirmation would connect the birth of luminous islands to events deeper than ordinary gravity. White hole streams would become the hidden rivers that nourish the first cities of stars, later masked by the bustle of cosmic time yet still visible in the way those cities are laid out. 33. The Milky Way and the question of a forgotten white hole phase. Our own galaxy carries scars of past activity, including bubbles of high-energy emission that tower above and below the disk. While often attributed to black hole outbursts, One can ask whether a brief white hole phase played a role in shaping these features. A transient emission from the centre could have injected cosmic rays and hot gas that inflated the observed structures. Such a phase would need to be short and rare to avoid contradictions with the steady environment required for long-term star formation. It would also need to leave behind matter distributions consistent with what we see in the bulge and halo. These constraints do not forbid the idea, but narrow its plausible forms to a single sharp episode rather than repeated events. Clues would include chemical fingerprints in halo stars that formed from gas influenced by the event. Enhanced ratios of certain elements and specific isotopes could point to a burst distinct from steady black hole feeding. Future spectroscopic surveys of ancient stars can search for such subtle patterns across the sky. Even if the answer is negative, the exercise forces a more precise reconstruction of the Milky Way's past. It reminds us that galaxies are not static museums, but living systems shaped by occasional upheavals. Asking the white hole question sharpens the models that explain why our home looks the way it does. 34. Particle creation in a white hole throat. Strong curvature can pull pairs of particles from the quantum vacuum, a process similar in spirit to Hawking radiation yet organized by outward flow rather than inward trapping. In the throat of a white hole, fields experience rapid changes that amplify fluctuations, turning virtual pairs into real particles that stream away with characteristic energies. The spectrum from this creation would not be purely thermal. It would carry peaks and valleys determined by the geometry and by any rotation or charge present. Measuring such structure would reveal the shape of the throat in a way that images cannot, much like how a musical instrument reveals its body through overtones. The data would be a sonogram of space-time. Interactions among the newborn particles complicate the signal. Collisions and magnetic fields can smear sharp features or shift energies before they escape. Careful modelling must include these effects to avoid misreading the cosmic music. A match between theory and observation would therefore be a strong confirmation rather than a fragile coincidence. If detected, particle creation in a white hole would complete a trilogy. Black holes show how horizons absorb. Cosmological expansion shows how horizons redshift. White holes would show how horizons release. Together they would present a unified portrait of how geometry sculpts quantum fields. 35. Do white holes reflect rather than absorb? Black holes are often described as perfect absorbers. The mirror image suggests a perfect reflector that refuses entry and hurls everything away. The truth is subtler. A white hole need not reflect like a polished surface. Instead, it denies inward trajectories altogether, which means that what appears as reflection is the insistence of geometry that only outward futures are allowed. This distinction matters for interpreting spectra and timing. A genuine mirror would return incoming signals with time-reversed copies, while a white hole would generate its own emission shaped by internal dynamics. Observers who mistake one for the other would predict incorrect correlations between incoming and outgoing light. Recognizing the difference ensures correct inferences about the engine at work. Laboratory analogues again offer insight. Systems that simulate horizons can be tuned between reflection-dominated and emission-dominated regimes. Watching how signals behave in these setups can teach which signatures belong to denial of entry and which to true bouncing. The lessons translate into search strategies for the sky. The broader moral is that names can mislead. Calling an object a white hole invites mirror images in the mind, yet the physics speaks a dialect all its own. Precision about what is forbidden and what is omitted keeps imagination tethered to law while leaving room for awe. 36. The second law of thermodynamics under white hole conditions. The second law asserts that total entropy does not decrease. White holes seem to challenge this by producing streams that may look unusually ordered. The resolution lies in hidden correlations. When all degrees of freedom are counted, including those that an observer does not measure, the total entropy can still rise even if visible order increases in one sector. This understanding reframes what a measurement really means. Entropy depends on which details are ignored, so a narrow measurement can give the illusion of violation. A full accounting restores the law. White holes then become laboratories where this subtlety is not a footnote but the main event. The streams they produce force careful bookkeeping rather than hand-waving. The horizon area law offers a complementary guide. For black holes, area behaves like entropy. For white holes, area evolution flips direction, challenging simple translations. A consistent theory must show how area, correlations, and emitted quanta conspire to maintain the global increase. Reaching that consistency is not optional. It is the price of calling the framework physics rather than speculation. Experiments will test pieces of this story by seeking fine structure in emissions and by comparing observed randomness with predictions that include correlation effects. Success would turn a philosophical law into an empirical triumph at the edge, where gravity and quantum theory meet. 37. Would a traveller survive a white hole outflow? The image of riding an outward torrent is compelling, yet survivability depends on gradients rather than on raw speed. Tidal forces near the horizon can stretch and compress with lethal intensity. A traveller would face a storm of radiation and particles that delivers more energy per second than any known shield can handle. Survival appears unlikely for human-scale bodies. There may exist regions farther out where forces have softened and densities have dropped. In those regions, a probe could sample the outflow briefly before being shoved to safer distances. Designing such a probe would require materials that shrug off high-energy impacts and instrumentation that records data in short bursts before components degrade. The mission profile would be sprint rather than marathon. Communication would be another hurdle. The outflow can scramble signals and sweep them outward faster than a steady transmitter can adjust. Practical plans would rely on robust one-way broadcast bursts timed to align with predicted windows of transparency. Even failure would teach lessons about the environment, since the way a signal dies carries information. Whether or not a traveller survives, the thought experiment clarifies the physics. The environment is not a gentle fountain. It is a structured gale shaped by geometry. To ask about survival is to force realistic estimates of gradients, densities, and timescales, which in turn guide what telescopes should expect to see. 38. Time measured inside a white hole compared to cosmic time. Proper time is the reading on a clock carried by an observer. Cosmic time is the shared coordinate used to chart the expansion of the universe. Near a white hole, proper time follows the traveller calmly, while cosmic time slices across the geometry in ways that can make events seem out of order. This mismatch breeds paradoxes only when the distinction is ignored. For the traveller, nothing ever runs backward. The sequence of experiences remains sensible. For distant observers who stitch events using cosmic time, the order can look inverted, as if outcomes precede origins. Both views are valid within their frameworks. The lesson is that time is not a single river, but a family of clocks, each bound to its path through space-time. This relativity of time has measurable consequences. Pulses emitted by the matter leaving a white hole would arrive in patterns that differ from expectations based on a single global clock. The intervals between pulses could shorten or lengthen in ways that map the geometry directly. Timing arrays that monitor many sources simultaneously would turn these variations into a three-dimensional portrait of the surrounding space-time. Bringing the two times into harmony requires models that translate between proper and cosmic measures without pitfalls. Success would replace paradox with prediction and would allow astronomers to read the time signature of a white hole as confidently as they now read the chirp of a merger. 39. Are white holes permanent or quantum flickers? Stability analysis suggests that ideal white holes may not endure. Slight disturbances can grow, pushing the system toward collapse or transformation. Quantum effects can either hasten the demise or delay it, depending on how they alter the throat. The upshot is that many realistic white holes might be brief, living only long enough to shout and fade. If brevity rules, the sky should hold a population of transients with clean starts and rapid finishes. Their statistics would follow the probabilities of quantum tunneling and evaporation, producing many small events and few large ones. Surveys designed for short timescales and wide coverage become the natural tools to catch them. Instruments that stare at single targets for long intervals would miss the fireworks. Conversely, if some white holes persist, they would shape their environments through steady outflows and distinctive lensing patterns. The absence of such steady signatures tilts the balance toward flickers, though it does not settle the question. Continued non-detection of persistent cases narrows the allowed lifetimes and guides theory toward short-lived solutions. Either outcome is informative. Flickers point to quantum rules that dominate near-extreme curvature. Permanence would reveal a stable new phase of space-time. In both cases, the search acts as a probe of the most fundamental physics available to observation. 40. How loop quantum gravity treats white holes. Loop quantum gravity replaces continuous geometry with discrete building blocks. In this framework, the singular interior of a black hole is resolved into a region where volume never reaches zero. The dynamics then permit a bounce that converts inward collapse into outward expansion. On the far side of the bounce, the solution behaves like a white hole that releases what was once trapped. This approach offers concrete predictions. The bounce sets a timescale that depends on mass, and the final emission carries correlations that reflect the discrete structure. For small primordial holes, the timescale can fall within the age of the universe, implying that some should complete their evolution today. The predicted signals are brief and energetic, aligning with the search for sharp transients. A virtue of the framework is that it keeps energy conditions conventional while altering geometry at the smallest scales. No exotic matter is required. The discrete nature of space supplies the pressure needed to halt collapse. The model also preserves information by mapping the internal state across the bounce into the outgoing radiation, answering the loss puzzle in a tangible way. Future progress will depend on matching these predictions with data. If instruments detect events with the expected timing and spectra, confidence in the discrete picture will grow. If they do not, parameters can be tightened or the approach revised. Either result advances the goal of turning white holes from mathematical curiosities into empirical science. 41. Spacetime mirrors and the symmetry between past and future. Einstein's equations do not favour one direction of time over the other. The symmetry hidden in them suggests that every process allowed by gravity in one temporal direction has a mirror version in the opposite. A white hole is the purest embodiment of this mirror principle, transforming the collapse that creates a black hole into an expansion that undoes it. The concept is not poetic flourish. It is mathematics describing a geometry that reverses the script of causality while maintaining perfect consistency. In this mirrored setting, the past and the future are not separate realms, but reflections across a single sheet of spacetime. Events near a white hole could correspond to reversed versions of processes occurring near black holes elsewhere. The geometry folds like origami, aligning one half with its inverted twin. Understanding this mirror symmetry might reveal why the fundamental laws appear reversible, even though experience insists otherwise. Observational traces of such symmetry would appear as correlated phenomena across vast distances or epochs. For instance, patterns in gravitational waves or background radiation could exhibit inverted copies of structures produced by black holes. Detecting those reflections would be like finding two halves of a cosmic photograph, each showing the same moment viewed from opposite sides of time. If nature truly uses this mirror symmetry, the boundary between creation and destruction blurs. What looks like an ending from one perspective could be a beginning from another. White holes would then stand not as anomalies, but as confirmation that the universe respects deeper balance, one that holds even when time itself seems to run out. 42. Are tachyons necessary for white hole kinematics? Tachyons are hypothetical particles that travel faster than light, usually invoked to describe processes involving negative time or reversed causality. Some early attempts to model white holes required tachyonic motion to explain how matter could emerge from a horizon faster than light seems to allow. Modern treatments suggest that such speeds are illusions created by geometry, not literal violations of relativity. Yet the question remains whether tachyons play a hidden role in sustaining outward motion. If tachyons exist, they could serve as mediators of time-reversed influence, transmitting information from the future collapse that seeds the white hole to its present emission. Their inclusion would make the process locally consistent while globally non-causal. This idea remains controversial, as it risks introducing paradoxes that physics works hard to avoid. Nonetheless, mathematical models of white hole metrics often contain tachyonic terms, implying that the geometry behaves as though such entities were present. Experimentally, no tachyon has ever been detected, but certain anomalies, superluminal neutrino hints, or phase velocities exceeding light in specialized media, keep curiosity alive. If even indirect evidence emerged, it could reshape how white holes are modeled, turning speculative mathematics into testable physics. Whether tachyons are real or simply bookkeeping tools, their appearance in white hole equations serves as a reminder that our intuitions about speed and time are products of limited perspective. Beyond those limits, the universe may allow patterns of motion that defy common sense, while still obeying deeper consistency. 43. The cosmic microwave background as a white hole afterglow. The cosmic microwave background, CMB, is the oldest light we can see, a nearly uniform bath of radiation left from the early universe. Its origin is usually tied to the moment matter and radiation decoupled after the Big Bang. But if that Big Bang was itself a white hole event, the CMB becomes the lingering echo of that expansion, radiation streaming from the surface of a time-reversed horizon that marked the universe's birth. This reinterpretation preserves all existing observations but changes their meaning. The faint ripples in the CMB, usually attributed to quantum fluctuations during inflation, would represent unevenness in the white hole's surface geometry. Each hot and cold patch would trace regions where the outflow expanded with slightly different intensity, fossilizing the curvature of the original horizon. Such a view predicts small but measurable correlations between the size of temperature fluctuations and their polarization patterns. Precision maps from satellites like Planck and future missions could test whether those correlations match white hole-derived models better than standard inflationary ones. If they do, the earliest light would no longer mark mere recombination. It would be the literal glow of space-time's reversal. Seeing the CMB as a white hole afterglow transforms it from background noise into evidence of cosmic metamorphosis. The universe itself would then be the radiation shell of an event still unfolding beyond our reach, an expanding memory of the instant when time's direction was chosen. 44. White holes that ignite new universes beyond our horizon. Every black hole hides a singularity where classical physics fails. If those singularities rebound as white holes, each could seed a new universe with its own space-time and physical constants. The process would resemble cosmic reproduction, where every collapse in one universe becomes an expansion in another. What we call the Big Bang could simply be the local version of such an event. This framework solves several long-standing puzzles at once. It explains the uniformity of the cosmos by suggesting that each new universe inherits smooth geometry from the compressed conditions of its parent. It also reconciles energy conservation, as what falls into a black hole here reappears as the material of a universe elsewhere. In effect, reality recycles itself infinitely through these connected births. Observationally, these daughter universes would be forever beyond reach, separated by causal boundaries. Yet their existence might influence our own through subtle statistical fingerprints. If physical constants vary across universes, the distribution we observe could reflect evolutionary selection favoring conditions that produce more black holes and thus more offspring. The image is grand and humbling. Every galaxy may contain not just countless stars, but as the seeds of countless new universes waiting to bloom. White holes in this view are not exotic exceptions, but the continuation of cosmic life in another domain. 45. The information paradox and a white hole escape route. The information paradox arises because black holes seem to erase details of what falls into them, contradicting quantum theory's rule that information is never lost. A white hole phase offers an elegant resolution. Instead of destroying information, the system stores it in deep curvature until the geometry reverses and releases it. The ledger remains balanced, though the transaction may take eons to complete. This perspective reshapes Hawking radiation's role. The slow evaporation seen from outside could be the preliminary phase of a transformation, with the final burst, a white hole emission, restoring the encoded information. The process would resemble a long delay rather than an irreversible deletion. From the universe's viewpoint, nothing is missing. Only we, bound by finite time, perceive loss. Mathematical studies using loop quantum gravity and holographic duality already support versions of this idea. They show that horizons can evolve continuously into outgoing structures that radiate in patterns consistent with preserved information. Subtle correlations in the radiation, minute departures from thermal uniformity, serve as the physical manifestation of recovery. If future detectors uncover these correlations, the paradox would dissolve into understanding. White holes would stand not as curiosities but as proof that quantum law and gravity never truly clash, only conceal their harmony behind the slow breathing of space-time. 46. Do white holes erase horizons by design? A black hole's horizon defines what cannot escape. A white hole's horizon defines what cannot enter. But some theories suggest that in transitioning from one to the other, the horizon itself may vanish. The geometry could momentarily flatten, turning what was once a one-way membrane into open space. This would allow information to stream freely for a brief interval before a new configuration forms. The erasure of the horizon is crucial for reconciling time symmetry. It ensures continuity between trapped and untrapped states without requiring singular behavior. In this short-lived phase, spacetime acts like a valve opening in reverse, converting stored curvature into radiation and particles. Once equilibrium is restored, the horizon reforms outward, sealing the process. Detecting such an erasure would be nearly impossible directly, as it might last less than a microsecond. However, its imprint could remain in the energy distribution of the emitted particles, a distinctive pattern with a sudden shift from trapped to free modes. Future high-speed detectors analyzing cosmic gamma bursts might catch these transitions by their abrupt cut-off frequencies. The concept also refines our understanding of horizons themselves. They are not eternal barriers, but temporary arrangements of geometry that change as spacetime evolves. White holes teach that even the most absolute boundaries can, under the right conditions, dissolve into transparency. 47. Could white holes form from dying stars under rare conditions? When massive stars collapse, they typically create black holes or neutron stars. Yet under extraordinary circumstances, extreme rotation, magnetic fields, or quantum pressure, a collapse might reverse before completion. The rebound could release stored energy explosively, producing a transient white hole. Such a process would blur the line between stellar death and cosmological birth. For this to happen, the star's core would need to reach densities where quantum gravity effects dominate before a stable horizon forms. If the bounce occurs quickly, the outward surge could expel matter at relativistic speeds, mimicking certain supernova classes that remain poorly understood. Observers might record a sudden symmetric burst lacking the asymmetries typical of conventional explosions. Computer simulations are beginning to explore these thresholds. By coupling general relativity with quantum pressure terms, researchers find narrow windows where a rebound is mathematically permitted. Whether nature actually occupies those windows is an open question, but if it does, some of the most energetic transients in the universe might already be the signatures of such white hole-like events. Discovering even one verified stellar origin white hole would collapse the gap between astrophysics and cosmology. It would mean that the same rules governing the universe's birth operate, in miniature, inside individual stars, turning stellar death into a rehearsal for cosmic creation. 48 jets that appear superluminal and a white hole reading. Astronomers sometimes observe jets of plasma seemingly moving faster than light from distant quasars and blazars. The usual explanation is geometric, an illusion caused by motion close to light speed directed toward us. Yet if a white hole were powering such jets, true superluminal behavior might emerge, not violating relativity but redefining the measurement of time within the expanding region. In a white hole frame, the outflow's internal clocks run opposite to those outside. This reversal can make outgoing material appear to outpace light's travel in our coordinates while remaining causal in its own. The result would be apparent superluminal expansion, a ghostly speeding up that our instruments interpret incorrectly because they assume a single arrow of time. Evidence could come from timing mismatches between jet bases and outer knots, where light emitted later appears to arrive earlier. Such inversions defy conventional models but fit neatly into a white hole framework. High-resolution radio observations already report puzzling timing anomalies that might merit reinterpretation. If confirmed, these jets would show that space-time can organize motion in ways that look impossible yet remain perfectly lawful. White holes would then stand revealed not only in the most distant reaches of the cosmos, but in the very phenomena that first signaled the existence of active galaxies. 49. Are white holes mathematical artifacts or physical realities? For decades, skeptics have argued that white holes exist only as solutions on paper, unstable and unreal in the physical universe. Yet many once mathematical constructs, black holes, gravitational waves, eventually found empirical support. The line between artifact and reality moves with observation, not ideology. White holes now stand where black holes once did, predicted, doubted, waiting for proof. To decide the issue, physics must answer two questions. Can white holes form through known processes, and can they persist long enough to be detected? The first concerns initial conditions, the second, stability. Advances in quantum gravity are closing both gaps, showing mechanisms that generate short-lived white holes from evaporation or rebound. These results hint that reality may host transient versions even if permanent ones never arise. Observation lags behind theory mainly because predicted signals are rare and fleeting. Unlike black holes, white holes leave no steady shadow to photograph. Their proof will come from timing, correlation, and statistical anomalies that resist all conventional explanations. With upcoming observatories designed for fast transients, the odds of discovery are improving. If those detections arrive, white holes will graduate from mathematical curiosities to physical citizens of the cosmos. The journey from equation to observation will again demonstrate that imagination disciplined by mathematics can anticipate nature by centuries. 50. The role of boundary conditions in producing white hole solutions. Every solution to Einstein's equations depends on boundary conditions, choices about what happens at the edges of spacetime. For black holes, the usual condition is collapse from finite matter distribution. For white holes, the inverse boundary is required, an initial state that begins with outward flux. Whether such a condition ever arises naturally is central to the debate over their reality. In numerical simulations, tweaking boundaries can produce stable white hole metrics that persist for chosen intervals. This shows that the mathematics itself imposes no ban. What matters is whether the universe's initial data include such configurations. Inflation, vacuum fluctuations, or quantum tunneling might occasionally generate them spontaneously. Boundary thinking reframes formation as a question of context rather than material cause. The geometry does not need an explosional mechanism in the classical sense. It simply requires spacetime to adopt an initial pattern where expansion dominates. Once that pattern exists, Einstein's equations carry it forward consistently without further assistance. Understanding these boundary conditions matters beyond white holes. It illuminates how universes themselves might originate and how apparent asymmetries, like a preferred arrow of time, emerge from otherwise symmetric laws. The margins of space-time, it turns out, may decide the play as surely as the actors within it. 51. Can white holes cool the vacuum or heat it? A white hole pours energy outward, but energy has many faces. It can manifest as heat, radiation, or changes in the state of the quantum vacuum itself. In classical terms, the outflow should heat its environment. Yet quantum field theory in curved spacetime offers a twist. When vacuum fluctuations are stretched by expansion, they can lose coherence, effectively cooling the surrounding field. Whether a white hole warms or chills the vacuum depends on the interplay between expansion rate and field coupling. If the outflow expands faster than light can communicate within it, modes of the quantum field are red-shifted beyond interaction. The energy density per unit volume drops, resembling cosmic cooling after the Big Bang. Conversely, slower expansion traps radiation, producing thermalization and a spike in local temperature. Both regimes could occur sequentially, an initial heating as curvature releases stored energy, followed by cooling as that energy dilutes across an enlarging volume. Observational consequences might appear in spectral distortions of background radiation near candidate regions. An unexpected suppression of high frequencies could betray vacuum cooling, while an excess would indicate trapped heat. Detecting either pattern would reveal how quantum fields respond when spacetime itself breathes outward. Such findings would carry deep implications. They would mean that temperature, normally a property of matter, is also a property of geometry. The vacuum could be heated or cooled not by friction or sunlight, but by the rhythm of spacetime reversing itself. White holes would thus become cosmic thermometers for the very fabric of reality. 52. Negative time regions and their physical meaning. The mathematics of relativity allows coordinate systems where time takes negative values, not as fantasy but as reflections of geometry's symmetry. In a white hole solution, some regions can be labelled with negative coordinate time relative to an external observer. This does not mean events run backward for local inhabitants. It means that the mapping between internal and external chronology flips sign. Understanding this distinction is crucial for interpreting any claim of time reversal. Within negative time regions, worldlings still progress forward locally. However, when drawn on global diagrams, they appear to point opposite to ordinary causality. Information flowing through such a region can exit into a universe whose timeline diverges from its origins. The mathematics preserves consistency. Every curve remains causal within its domain. But global observers cannot reconcile the order of events without acknowledging multiple time orientations. Such regions may arise not only in white holes, but in rotating or charged spacetimes where horizons intersect. They form pockets where the arrow of time momentarily loses universal alignment. No paradox follows because interactions remain local. What changes is the bookkeeping of before and after across boundaries. Exploring negative time zones extends relativity from a theory about motion to a theory about the architecture of causality itself. It suggests that time's direction is not absolute but patchwork, stitched together by geometry. White holes, by hosting these regions, show that even time can have edges and seams where the fabric of existence turns inside out. 53 are white holes required if time is fundamentally symmetric. If the universe's laws are truly symmetric under time reversal, every process that leads to a black hole must have an opposite counterpart. In such a world, white holes are not optional decorations, they are the necessary mirror images that keep the ledger balanced. The absence of observed examples would then call for an explanation of how symmetry breaks, not whether it exists. Quantum mechanics adds nuance. While most microscopic interactions respect time symmetry, measurement, and thermodynamic irreversibility appear to favour one direction. White holes might represent the restoration of that lost balance on cosmic scales, where geometry enforces what local processes forget. Their rarity could stem from initial conditions that overwhelmingly favoured collapse over expansion, rather than from any ban in the equations. Philosophically, this argument flips a common intuition. Instead of asking why white holes exist, one asks why they do not flood the cosmos if symmetry reigns. Perhaps they do exist, but in domains where entropy is so high that their effects are diluted, or perhaps they manifest only as quantum echoes in evaporation events. Either way, their presence maintains the mathematical dignity of time symmetry. In that sense, white holes are less exotic than expected. They are placeholders for a cosmic balance sheet. Their existence, even if only implicit, ensures that the universe's equations remain honest, paying back every debt of asymmetry with an equivalent act of reversal somewhere beyond our view. 54. White holes inside laboratories of thought experiments. Because no confirmed white hole has yet been observed, laboratories of the mind serve as their first testing grounds. Physicists design analog systems where equations mimic the essential behaviour: fluids flowing faster than wave speed, optical media with refractive horizons, or superconducting circuits that simulate curved spacetime. These analogues allow hands-on exploration of what emission and time reversal might mean under controlled conditions. In such setups, waves play the role of matter, and changes in flow simulate expanding geometry. Experiments have reproduced effects akin to Hawking radiation, proving that horizon thermodynamics is not limited to celestial scales. Extending these analogues to white hole conditions, where the horizon expels rather than absorbs waves, reveals new behaviours such as stimulated emission and amplification of background noise. Results show that the reversal is stable only in narrow regimes. Too strong an outflow and turbulence destroys the pattern. Too weak and the analogy collapses into triviality. Yet even these difficulties teach valuable lessons. They indicate that the physics of horizons depends more on relative motion and boundary coherence than on cosmic scale. By building white holes in miniature, researchers transform metaphysical speculation into empirical craft. Each laboratory success brings the concept closer to tangible reality, proving that understanding the cosmos sometimes begins not in distant galaxies, but in quiet rooms filled with lasers, fluids, and imagination disciplined by math. 55. Quantum tunneling paths from black to white. Quantum tunneling allows systems to cross barriers that classical physics forbids. A black hole transitioning into a white hole could be such a process, with the barrier being the singularity itself. In this view, the collapse does not end in oblivion, but tunnels through to an expanding configuration, conserving total energy and information while violating classical expectations of permanence. The probability of tunneling is minuscule for large black holes, but increases as they evaporate. When the mass shrinks to near the Planck scale, the barrier thins enough for the transition to occur. The resulting event would look like an explosive release of the final stored energy, consistent with certain high-energy astrophysical bursts that remain unexplained. Mathematically, tunneling replaces singularities with continuous trajectories in complex spacetime, paths that dip below the real axis and return. These trajectories are well-behaved, meaning the theory retains unitarity and avoids infinite densities. The universe trades certainty for possibility. Everything that can happen, given enough time, eventually does. This mechanism unites the seemingly opposite fates of collapse and expansion. Black holes become cocoons rather than graves, incubating future emission states. The laws of quantum mechanics, applied to geometry itself, turn inevitability into evolution, making white holes not exceptions but natural outcomes of spacetime's restless curiosity. 56. Are white holes compatible with cosmic censorship? The cosmic censorship conjecture posits that singularities must remain hidden behind horizons, shielding the universe from naked infinities. At first glance, white holes appear to violate this rule by spewing material from singular points. However, when treated carefully, they do not expose infinities, they transform them. The interior remains shielded by an outgoing horizon that enforces causal order from the inside out. If censorship holds, any physical white hole must emerge only when quantum effects smooth the singularity into a finite region. The event would then preserve cosmic modesty while still releasing energy. Numerical studies show that such transitions can occur without exposing naked singularities, maintaining the conjecture's dignity even in reversal. On the other hand, if observations ever revealed emissions inconsistent with any enclosing horizon, censorship would face its first real counterexample. That outcome would force a rewrite of relativity's unwritten rulebook, admitting that the universe occasionally lets its deep structures show. Such transparency would not destroy physics, but enrich it, revealing what the law was protecting us from. Thus, white holes stand as both test and teacher. If they obey cosmic censorship, they demonstrate the theory's resilience. If they do not, they unveil the hidden layers beneath, where gravity's secrets no longer require polite veils to be profound. 57. Entropy bookkeeping when matter re-emerges from a white hole. Every physical system carries entropy, and accounting for it across extreme transformations is essential. When matter escapes a white hole, its entropy must match or exceed that of the initial state to respect thermodynamic law. The process seems paradoxical. A black hole swallows high-entropy material into order, while a white hole expels ordered radiation into chaos. Proper bookkeeping reconciles the two. The key lies in correlations. Information about what entered the black hole is embedded in correlations among outgoing particles from the white hole. Though the particles appear random individually, the entire ensemble encodes a structured pattern with total entropy balanced. To observers lacking full access to all data, the emission looks thermal and entropic, but globally the system's entropy never decreases. This subtle accounting resembles quantum error correction, where global coherence hides beneath local noise. Holographic duality supports this by showing that information at a boundary can store everything within a volume. A white hole is essentially the playback of that hologram, projecting stored data back into the world through radiant complexity. By mastering this entropy ledger, physicists bridge the gulf between thermodynamics and information theory. White holes become the universe's accountants, proving that even when matter and time reverse, the books still balance perfectly down to the last quantum digit. 58. Do white holes radiate patterns that encode the past? If a white hole releases material once swallowed by a black hole, the outflow should contain memory, encoded patterns revealing the history of what went in. Unlike ordinary radiation, which is thermal and forgetful, this emission would bear correlations linking distant moments and frequencies. Detecting such structure would be the ultimate archaeological act, reading the fossilized story of a past universe written in light. The challenge lies in decoding that memory. Quantum correlations are delicate. Any interference erases them. Yet modern instruments can analyze photon statistics with precision unthinkable a decade ago. Deviations from purely random distributions in gamma bursts or cosmic rays could be the first hints of an encoded message from time's other side. The patterns would not spell sentences, they would manifest as rhythm, repeated ratios, harmonics, or phase alignments impossible to produce by chance. Each would mark the reappearance of entangled states once trapped behind horizons. Analyzing them requires both computational power and a new philosophy of interpretation, one that treats noise as narrative. If found, these signatures would confirm that nothing vanishes from the universe's memory. The past would not be gone, it would merely be recited in a new key, sung by light freed from the prison of gravity. 59. Could white holes shape the multiverse network? If every black hole births a white hole in another domain, then the cosmos becomes a network of universes linked by these events. Each node in the network would be a space-time, each connection a bridge of information. The overall structure might resemble a cosmic web far grander than the one traced by galaxies, a meta-architecture of realities feeding one another eternally. This network could explain apparent fine-tuning in physical constants. Universes producing more black holes would generate more offspring, and those offspring would inherit similar parameters. Over vast evolutionary times, this process would favor stable, life-supporting universes simply because they replicate better. The result is natural selection on a cosmic scale without the need for external design. Mathematically, such a network would be described by equations akin to branching processes in biology or information theory. Each generation of universes would carry mutations, slight differences in curvature, constants, or dimensions that determine their reproductive success. White holes serve as the reproductive organs of existence, ensuring continuity of structure across eternity. While this remains speculation, it reframes cosmology as an evolutionary science. The multiverse would not be a chaotic sea, but an organized lineage, with white holes as the engines of inheritance that keep the infinite family alive. 60. How white holes might end if they ever begin. The life cycle of a white hole may be shorter than any star, planet, or even particle lifetime known to physics. Once the outflow begins, conservation of energy demands that its reservoir must eventually run dry. Unlike black holes, which grow by accretion, white holes spend their existence giving away mass, momentum, and information. The process cannot last indefinitely. Geometry itself reshapes as the reservoir depletes. Eventually, the outward push softens, the horizon dissolves, and the object merges with surrounding spacetime, leaving only faint radiation as a ghostly memory. In some theoretical scenarios, quantum feedback accelerates this demise. As the outflow expands, the curvature at the center decreases, robbing the white hole of the very tension that sustains its reversal. When curvature drops below a threshold, the geometry relaxes, and the event horizon fades into transparency. What remains is a cloud of low-energy photons and particles drifting through interstellar vacuum, barely distinguishable from ordinary background radiation. Another possibility is oscillation. Instead of dying outright, a white hole could alternate between faint inflow and outflow phases on microscopic scales. To an outside observer, it would resemble a shimmer in spacetime, a pulse of reversible geometry that never truly settles. This scenario connects to proposals in loop quantum gravity, where discrete spacetime units can bounce repeatedly, producing quasi-stable remnants that flicker across eternity. Whatever its finale, the ending of a white hole carries philosophical weight. It implies that even reversal has limits, that time's defiance cannot persist forever. Every eruption, however grand, eventually blends into equilibrium. In that silence, the universe seems to reclaim its symmetry, one more breath in an infinite rhythm of expansion and rest. 61. Observational campaigns designed to catch a white hole in real time. Detecting a white hole demands an unconventional strategy. Traditional telescopes look for steady sources, but a white hole would likely manifest as a fleeting singular event, a burst of energy that appears from empty space and vanishes within seconds. The first requirement, therefore, is speed. Networks of wide-field observatories that scan the sky continuously, capturing millisecond transients, offer the best chance. Instruments like the Vera Rubin Observatory and space missions monitoring gamma and radio bursts could, by sheer vigilance, witness one. Coordinated observation across the electromagnetic spectrum is vital. A true white hole event would emit not just visible or gamma radiation, but a correlated sequence of signals: radio, X-ray, neutrinos, and perhaps gravitational waves. Real-time alerts allowing telescopes to pivot instantly could capture this full profile, the celestial equivalent of a forensic recording of cosmic birth. Machine learning plays a growing role here. Algorithms trained on the signatures of known phenomena, supernovae, pulsars, mergers, can filter out familiar events, leaving behind anomalies that defy classification. These unclaimed signals, short and structureless, are the prime suspects. By cataloguing them and searching for repeating patterns or geometric correlations, researchers might isolate the fingerprints of genuine white hole emissions. The goal is no longer merely to confirm existence, but to capture evolution. The first frames of data from such an event would rewrite textbooks, forcing cosmology to update its models of time, energy, and information. A single verified detection would bridge the imaginary with the observable, showing that space-time itself, occasionally blinks, and when it does, we can catch it. 62. Can white holes explain early supermassive black holes indirectly? One of astronomy's deepest mysteries is how supermassive black holes formed so quickly after the Big Bang. Some appear less than 1 billion years old, yet their masses exceed 1 billion suns. Conventional accretion models struggle to explain this pace. White holes might offer an indirect solution. Instead of forming from stars, the earliest black holes could be residues of previous cosmic cycles, leftover throats of white holes that have since inverted back into gravitational wells. In this vision, what began as outward explosions in a previous universe later reappeared as inward collapses in ours. The transition between cycles left compact, massive seeds already in place, ready to feed on surrounding gas and grow into the colossi we now observe. Their apparent youth would thus be an illusion born of inherited structure. Such relics would display unusual properties. Their spins might differ from ordinary black holes, reflecting the geometry of their previous expansion. They might also lack the chemical signatures expected from stellar ancestry. Detecting these discrepancies through high-resolution spectroscopy and gravitational wave analysis could provide indirect evidence of white hole lineage. If confirmed, this hypothesis would mean that the first supermassive black holes were not born within our cosmic timeline, but carried across from a prior era, a handoff between universes that preserves continuity across cosmic rebirths. What we call ancient would then be the youngest chapter in an eternal story of alternating collapse and creation. 63. The role of initial conditions at singularities turned inside out. Every cosmological model begins with initial conditions, values defining density, curvature, and temperature. In black holes, these conditions compress into a singularity. In white holes, they expand outwards as the seeds of structure. Turning the singularity inside out transforms a point of ignorance into a point of definition. What once marked the limit of physics becomes the starting line for everything that follows. This inversion raises an essential question. If a white hole truly begins where a black hole ends, then what determines the qualities of that reversal? Are they random or inherited from the collapsing phase? In theories that conserve information, the latter must hold. The white hole's first moments encode the memory of everything that fell into its precursor. The result is a universe sculpted by the final state of another. Understanding these initial conditions could explain cosmic uniformity without fine-tuning. A collapsing system naturally smooths irregularities. Its rebound would begin already homogenized. Thus, the remarkably even distribution of matter in our universe might simply be a geometric after-effect of a prior collapse. When singularities are treated not as failures but as transitions, cosmology gains both continuity and logic. The universe stops being an exception to its own rules. Instead, it becomes a perpetual act of inversion, each ending sculpting the symmetry of what follows, each white hole rewriting the script of beginnings. 64. White holes and violations of charge parity, time, symmetry, and subtle form. The combined symmetry of charge, parity, and time, known as CPT symmetry, is a cornerstone of modern physics. It states that flipping all three at once yields identical laws. Yet tiny violations have been suspected in particle interactions and cosmological data. White holes may be the grand theatre where such violations become geometrical rather than quantum. Their existence would mean the universe hosts regions where time's orientation, and therefore CPT balance, locally deviates from the rest. Within a white hole, reversal of temporal direction acts as a partial CPT transformation. The resulting spacetime might favour antimatter production, or alter the polarization of emitted radiation in ways detectable from afar. Some astrophysical anomalies, excess positrons, asymmetrical neutrino fluxes, could trace back to such geometrical biases rather than exotic particles. The key is that CPT need not fail globally, it can bend locally. Just as magnetism flips direction across poles, spacetime may allow regions where symmetry inverts only for moments before reconciling. The overall universe stays balanced, but the path to balance includes asymmetrical steps. If these violations were measured, say through specific circular polarizations and gamma-ray bursts, they would confirm that geometry participates in the same subtle asymmetries known from quantum Hawking fields. White holes would then be not only cosmic phenomena, but living laboratories of broken symmetry, revealing how nature hides imbalance inside perfect mathematical order. 65. Do white holes require a preferred cosmic time? Einstein's relativity denies the existence of universal time. Each observer measures their own flow. Yet white holes seem to demand a reference clock, a sense of direction defining inside from outside. Without such a preferred time, how can reversal even be defined? The paradox dissolves only if white holes select their own internal time, an emergent arrow that locally breaks relativity's democratic rule. This intrinsic clock could arise from entropy gradients or quantum coherence within the outflow. The moment expansion begins, conditions inside differ irreversibly from those outside, establishing a temporal hierarchy. For distant observers, that clock might appear misaligned or even reversed, but within the system, it defines order as reliably as any sun marking day from night. The idea challenges relativity not by refuting it, but by extending it. If white holes generate their own temporal frames, then time is no longer universal nor entirely relative. It becomes contextual, an attribute of geometry itself. Each region of spacetime could host its own tempo, harmonizing or clashing with its neighbors like instruments in a cosmic symphony. Detecting evidence of such local time might involve analyzing frequency drifts in radiation emitted during expansion. Subtle inconsistencies between measured and predicted time dilation could hint that white holes carry their own clockwork, ticking to a rhythm set by the reversal of spacetime rather than the pulse of the cosmos. 66. Are white holes hidden inside black hole interiors as future states? Some versions of quantum gravity suggest that every black hole secretly contains the seed of its own future white hole. Deep inside the horizon, where classical relativity predicts infinite collapse, quantum effects could halt compression and initiate a slow transformation. Over eons, this internal kernel would evolve into a white hole state, waiting to emerge once the external horizon evaporates away. From an outside perspective, the process appears frozen. Time dilation near the horizon stretches the transformation almost indefinitely. To an observer within, however, the evolution proceeds normally. Collapse halts, reverses, and expansion begins. The black hole's death in one frame is the white hole's birth in another. Both exist simultaneously, divided by the relativity's warped sense of duration. This model eliminates singularities altogether. Instead of infinite curvature, there is a smooth bounce bridging two phases of spacetime, implosion and explosion, past and future. Each black hole becomes a chrysalis, and every white hole the butterfly it releases, though the metamorphosis spans cosmic ages. If correct, our universe teems with unborn white holes, each silently gestating within existing black holes. Their eventual emergence would mark not destruction but renewal, ensuring that even the darkest corners of the cosmos harbour the seeds of creation waiting for their appointed time. 67 toward white hole chemistry of primordial element synthesis. The first atoms of hydrogen, helium and lithium are believed to have formed minutes after the Big Bang during a period called nucleosynthesis. Yet if the universe itself was born from a white hole, that ancient chemistry might not have been limited to one event. Each white hole eruption, large or small, could carry within its expanding plasma a miniature version of cosmic nucleosynthesis, producing light elements in the furnace of its rapid expansion. In this view, chemistry is not a passive product of the cosmos. It is an inheritance from repeated acts of spacetime renewal. The mechanics are straightforward but profound. As a white hole expands, temperature and density drop through precisely the range where nuclear reactions balance between fusion and freeze-out. The same conditions that shape the first helium could repeat on smaller scales, meaning each eruption leaves behind a trail of newly minted elements. Over cosmic time, these microcosmic forges could subtly enrich intergalactic space long before the first stars lit up, seeding the raw material for galaxies to come. Detecting such primordial fingerprints would require spectroscopy of the most pristine gas clouds in the universe. Slight anomalies in isotopic ratios, such as unusual deuterium to hydrogen balances, or trace lithium overproduction, might betray contributions from non-cosmological nucleosynthesis. These ratios act as fossils, whispering that creation has happened more than once and in more than one place. If confirmed, white holes would no longer be abstract geometry but active chemical agents in cosmic history. Every atom in your body could trace its ancestry not only to stars but to the expanding throats of reverse time. chemistry would become the permanent signature of spacetime's recurring act of self-expression. 68. The fate of antimatter near a white hole mouth. Antimatter is fragile in our universe, annihilating whenever it meets ordinary matter. But near a white hole, where energy densities soar and time reverses direction locally, annihilation dynamics may change dramatically. In certain configurations, antimatter could survive longer, protected by the geometry that accelerates it outward faster than it can collide with normal particles. The mouth of a white hole might therefore act as a selective filter, favouring antimatter emission over matter under specific conditions. This asymmetry could help explain why our universe is dominated by matter. If ancient white holes preferentially expelled antimatter into regions that later became isolated or hidden behind other horizons, what remained visible to us would naturally be matter-rich. The so-called baryon asymmetry problem, which has haunted cosmology for decades, might be a consequence of geometric sorting rather than microphysical bias. Experimental evidence for this scenario could come from space-based detectors looking for localized excesses of positrons or antiprotons without matching matter partners. Some of these anomalies have already been reported near galactic centers and cosmic ray belts, though their sources remain debated. A white hole origin would unify them into a coherent story, relic emissions from space-time's earliest expulsions. Beyond physics, the idea reframes balance itself. It suggests that matter and antimatter are not eternal enemies but complementary outcomes of time running in opposite directions. White holes, through their geometry, may have drawn the cosmic line that separated what falls inward from what escapes forever outward. 69. White holes and the emergence of order from high compression. Ordinarily, compression breeds chaos. Molecules collide, heat rises, and structure dissolves. Yet at the heart of gravity, the opposite may occur. Under the crushing density that precedes a white hole's birth, matter loses individuality and transitions into pure geometry. When the rebound comes, that geometry re-expands into ordered motion, carrying the imprint of its symmetry into the surrounding universe. What begins as collapse ends as coherence. This emergence of order from compression echoes across physical law. In quantum systems, extreme confinement produces discrete stable energy levels. In thermodynamics, phase transitions bring new organization. White holes represent the gravitational analog, collapse distilled to its simplest form, expansion structured by that purity. Their outflows could thus carry the rhythm of the very equations that birthed them, making the early universe's smoothness a direct expression of geometric order. Observationally, this might explain why cosmic background radiation is so uniform despite originating from violent beginnings. The compression phase that preceded expansion erased turbulence, leaving behind a perfect template for balance. The white hole model predicts slight deviations only where curvature gradients differed, precisely matching the faint anisotropies observed today. Seen this way, a white hole is not an explosion but a crystallization of time and space, a furnace that purifies disorder into pattern. In its aftermath, galaxies, stars, and life arise as echoes of that single moment when chaos bowed to structure and expansion became the language of symmetry. 70. Computational universe views where white holes rewrite data. In digital physics, the universe is seen as a computation, a grand information process running on the substrate of space-time. Within that framework, black holes act as data compressors, reducing information into highly dense storage codes. White holes, by contrast, would be the decompression algorithms executing the release, reformatting, and redistribution of those stored patterns back into reality. They would not destroy or create data, but reorganize it in new forms, preserving informational continuity while altering expression. This analogy gains depth when tied to holographic principles. A black hole's surface encodes its contents as a two-dimensional information map. A white hole would read that map backward, projecting the data outward into new spacetime regions. The flow of bits from compression to decompression mirrors the cosmic flow from collapse to creation. What we call time might simply be the direction in which this computation unfolds, forward during compression, backward during expansion. If the cosmos truly computes, then white holes are the system's debugging routines. Their emissions could represent corrections to informational imbalances introduced by prior collapses. Radiation patterns from these events might exhibit algorithmic complexity distinct from random noise, structured, recursive, and self-similar. Detecting such statistical features in high-energy astrophysical data would be equivalent to glimpsing the code behind reality's interface. Ultimately, the computational model of white holes invites humility. It suggests that every act of cosmic reversal is not chaos, but recalculation. In that light, the universe ceases to be a stage of accidents and becomes a processor of meaning, rewriting itself endlessly through the mirrored operations of black holes and white holes alike. 71. White holes in modified gravity proposals. General relativity has passed every test within reach, yet it may not be complete. Modified gravity theories, from Einstein-Cartan models with spin curvature coupling to F of R and scalar tensor formulations, introduce corrections that could make white holes more stable or more frequent. In some, torsion or extra dimensions prevent singularities entirely, forcing every collapse to rebound. The outcome is a cosmos populated with natural white holes, not mathematical rarities. In these frameworks, space-time acquires elasticity. Instead of snapping under pressure, it twists and stores energy like a coiled spring. Once limits are reached, that energy releases explosively as expansion. The resulting object behaves exactly like a white hole, but arises inevitably from the field equations themselves. Collapse and rebound become two faces of a continuous motion, not separate phenomena. Observational footprints of modified gravity might already exist. Deviations in the distribution of dark matter, unexpected acceleration patterns in galaxies, or anomalies in gravitational lensing could all stem from geometric corrections that favor rebound physics. Analyzing such data under the assumption of hidden white hole-like structures could reinterpret entire classes of cosmic puzzles without invoking invisible particles. If confirmed, modified gravity would show that the universe dislikes dead ends. Every path of collapse eventually folds back into expression. In this world, white holes are not exceptions but the natural exhalations of space-time, the inevitable breath after gravity's deepest inhale. 72. Could a white hole appear as a shadowless glare? Black holes are famous for their shadows, dark voids against luminous backdrops where light cannot escape. A white hole, being the opposite, might produce a spectacle just as distinctive, a glare with no visible source so bright and pure that it casts no shadow at all. Such an object would not look like a star or quasar, but like a blank wound of light, a hole of brightness rather than darkness. The physics behind this effect lies in how light interacts with the horizon. In a black hole, rays curve inward and vanish. In a white hole, they curve outward faster than they can cross paths, preventing the formation of a silhouette. The result is an optical paradox, intense luminosity without discernible edges, like an inverse eclipse expanding instead of obscuring. Detecting such glare would require instruments capable of handling extreme dynamic range without saturation. Deep field observations might already contain candidates dismissed as instrumental artifacts because they lacked coherent structure. Re-examining archival data with the expectation of radiant voids rather than dark ones could reveal the first hints. Should one be confirmed, astronomy would meet its first object defined by the absence of shadow. It would prove that the geometry of space-time can shine, literally, through the very mechanism that, in its mirror form, hides light forever. 73. Memory effects in gravitational fields left by white hole blasts. When gravitational waves pass through more space, they leave behind tiny permanent displacements known as memory effects. If a white hole were to erupt, its expanding geometry would broadcast a pulse of space-time itself, imprinting a measurable pattern on anything it touches. Unlike typical gravitational waves from mergers that oscillate and fade, a white hole's memory would act like a permanent fingerprint, a silent rearrangement of reality that never returns to its original configuration. This residual shift could persist across astronomical distances. Space would stretch minutely in one direction and remain that way forever, encoded into the positioning of stars and interstellar plasma. Sensitive detectors like LIGO and pulsar timing arrays could, in principle, detect these offsets as one-time jumps in phase rather than periodic waves. The difficulty lies in differentiating them from instrumental drift, but statistical consistency across detectors could reveal their cosmic origin. If such a memory were found, it would signify that space-time records its own history, Every burst, every expansion would leave a structural scar, a permanent retelling of the event. The universe would be more than dynamic, it would be cumulative, carrying its past not in light but in geometry. White holes, then, become authors of the universe's gravitational diary. Each eruption writes a line in that invisible script, and every atom, every orbiting planet, carries a subtle echo of those long-forgotten moments when space-time itself pulsed outward in memory of its own reversal. 74. Are some high-energy neutrino bursts white hole footprints? Neutrinos are cosmic messengers that rarely interact, allowing them to travel vast distances unaltered. In recent years, detectors buried deep in Antarctic ice have recorded bursts of ultra-high-energy neutrinos that defy known astrophysical explanations. Could these ghostly visitors be fragments of white hole outflows, relic particles from explosions where geometry itself expelled matter into the universe's deep past? The energies involved support the idea. White hole scenarios predict bursts of particles with nearly featureless spectra extending beyond the reach of supernovae or black hole accretion disks. Unlike photons, these neutrinos would carry directional memory of their origin, offering a straight-line signature to the region of spacetime that produced them. The fact that some detected events appear to rise from below the horizon, seemingly travelling through the Earth, adds to the mystery, hinting at origins beyond conventional timeframes. If white holes are the source, these neutrinos may not even belong entirely to our timeline. Their trajectories could intersect ours from geometries outside standard causality, giving the illusion of upward motion through the planet. Modelling their arrival patterns within a framework that includes temporal inversion could explain these paradoxes without invoking new particles or impossible sources. Should further detections align spatially or statistically with such predictions, neutrino astronomy would become the first direct observational science of space-time reversal. Each detected particle would be a traveller from the far side of time, an emissary of a brief white hole heartbeat that still reverberates across cosmic history. White holes may be the universe's most astonishing promise, that nothing truly ends, it only reverses. They turn collapse into renewal, silence into release, and disappearance into transformation. If they exist, then time itself is not a straight path but a vast breathing cycle, pulsing between black holes that absorb and white holes that exhale. The cosmos would no longer be a fading fire sliding towards stillness, but a self-renewing organism, inhaling matter into darkness and exhaling it back into light. Each eruption would represent the instant when gravity's grip surrenders to expansion, when what once seemed final becomes the first note of a new creation. In their dazzling defiance, white holes hint that the universe is not running out of meaning, it is recycling it. They suggest that memory, energy and form are preserved beneath the surface of apparent loss, waiting to return in different guises across eons. To contemplate them is to sense a profound symmetry underlying everything, that creation and destruction are not opposites, but phases of one eternal pulse. What falls inward somewhere may already be rising outward elsewhere, carrying the echoes of all that ever was, proving that even in the deepest silence of space the universe is never finished speaking. White holes whisper that the cosmos may be far more conscious of itself than we imagine, an endless intelligence folding and unfolding through gravity's rhythm. They blur the boundary between life and decay, between before and after, suggesting that time itself might simply be a motion of return. In their unseen brilliance, they promise that every collapse is secretly a preparation for renewal, every seance a gathering of energy before the next burst of creation. Perhaps the light that vanished into darkness long ago is already emerging somewhere beyond our reach, rewritten by the geometry of time, and if that is true, then the universe is not merely expanding, it is remembering endlessly, beautifully, and without end. White holes remind us that even the void has purpose, that absence itself may be a kind of creation in progress. In their quiet defiance of finality, they offer a single, breathtaking truth: the universe never stops becoming. And as we drift deeper into that cosmic stillness, we may sense that every ending we fear is only the universe pausing to breathe before it begins again. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand that strangeness.